Okay, so 4.4, day 2 examples. My first one is, if a rectangle has an area of 100, what are the dimensions of the rectangle such that the perimeter is the minimum? So if you watch the video, I did an example where I gave you a fixed perimeter and we maximized the area, I believe. And this is a little bit different. Here I'm giving you a fixed area and we're trying to minimize the perimeter. So here's what's going on. You've got a rectangle, right? And it has an area of 100, like that. It might look like this, but it might not. It might actually just be a square. After all, a square is part of the rectangle family. So I've drawn two possible drawings here. Of these two, which one do you think would have the lesser perimeter? Square. The square? Rectangle. Okay, so it's kind of a toss-up maybe. Maybe if I exaggerate my rectangle a little bit. Why don't we exaggerate our rectangle? This looks like it might be like a, I don't know, 20 by 5 rectangle or something. That's why its area is 100. But what if I drew it like this, and I drew a 100 by 1 rectangle? That has an area of 100 square centimeters. I think you'd realize, wow, my perimeter is 202 here, whereas down on this picture, the perimeter is only 40, see? 10, 10, 10, 10, but this one is 100, 100. Why am I saying 100? Yeah, 100, 100, 1, 1, that's 202. That's a lot of perimeter. So it seems like the square should have the least possible perimeter. Maybe you took an SAT class where they taught you that when you're given a fixed area, the regular polygon is the one with the least perimeter. Did anyone ever learn that? It's a great skill for the SAT. We're going to prove that right now. Okay, so let's go ahead and try just drawing a random rectangle. We're going to assume it's random. And this will be x and this will be y. And the area is 100 square centimeters. So I usually start off with some kind of a picture like this. And then I write down the facts. What is the fact they gave me? They said the area is 100. So you can write xy equals 100. This is just given. Now I want to write down the primary equation. So if you watch the video, you know that a primary equation is just the equation of the thing you're trying to optimize. We are trying to do perimeter minimum. Perimeter minimum. So perimeter is the function we would use. So let's write down the perimeter. What is the perimeter function? 2x plus 2y. Has nothing to do with area at all, right? Totally different idea. 2 x's and 2 y's. Okay? This is our primary equation. Let's get it in one variable. So in order to get this in one variable, we cannot have two variables. So how are we going to get rid of y? Well, if you go back up to the given fact, you can think of this as y equals 100 over x. And if we substitute that into our primary equation, we can see we really did get it into one variable. It is always possible to get your primary equation into one variable on the problems in this textbook. Okay? Okay, this might have been the hardest part, just getting this to this phase. The rest is basic calculus. So here's our function, basically. We have 2x plus 200, x to the minus 1. And the rest, you're just going to take the derivative, set it equal to 0, solve for x, that sort of thing. But before you do that, you need to write down what a meaningful value of x would be. Okay? Because this is real life stuff. And so we need a meaningful constraint for x. Like, what is x? In this diagram, what does x represent? What does it mean? What? The width. Okay. Some people say that's the length, width, whatever. Right? It's a side length. So we know it has to be a positive number. Does everyone agree with that? Okay. So a meaningful constraint for x here would be x is greater than 0. It's kind of a domain thing. There's no meaning to negative x's. Even 0 doesn't make much sense. So we're going to assume that x is a positive number. Now we'll jump into the calculus. Okay, so we find the derivative. P prime of x is 2 minus 200 x to the minus 2. And this is good for any x's that are positive. Just a little side note there. And we want critical points. So set P prime of x equal to 0. And you can add the 200 x to the minus 2 to this side. So that was, the red is calculus. Took the derivative. So basically I have 200 over x squared equals 2. Or you could say 200 equals 2x. Bless you. 200 equals 2x squared. I think it's pretty obvious x is 10. Technically it's plus or minus 10, but we already said x is greater than 0, right? Okay, so x is 10 centimeters. X is 10 centimeters. So what does that mean? Well, remember our perimeter was, our drawing looked like this. And we had an x here and a y here, remember that? So we had also said that y is basically 100 over x. So now that we know what x is, what's 100 over 10? 10. Okay, so y is also 10 centimeters, and we see that really is the case of a perfect square. So what your SAT teacher taught you is true, that when you have a fixed area like this, and you're trying to wrestle to find the smallest perimeter, it has to be the regular polygon. That'd be the square in the case of quadrilateral. So it's not a hard problem at all. Now, just real quick, when the derivative is 0, does that mean that it is a minimum? No. Not necessarily. So we just solved this whole problem by assuming p prime equals 0, right? And that led us to believe that x was 10. But how do we know that's actually a minimum? Because a function can have derivative 0 at a maximum too, right? So just real quick, we're just going to just do a quick sign chart to confirm that this really is a minimum. So let's just draw a quick sign chart. We believe 10 is the magic number, x equals 10. And we know that you can't go to the left of 0, so I usually draw a number line like this for my sign chart. So there's my critical point right there. Let's plug in, let's say, into our derivative. Let's plug in, I don't know, 1. If you plug in 1, this is going to come out to be what? Negative. It's 200 minus 200. I'm sorry, 2 minus 200. But if you plug in a number to the right of 10, this is going to come out to be positive, because it's 2 minus 200 over x squared. So if you plug in, say, x equals 10, for example, it comes out to 0. But if you plug in x equals, say, 20, it's going to come out to like 1.5. So this is positive on this side. So it really was a minimum. The derivative changed from negative to positive. We just wanted to confirm that. Okay, notice the question actually asked, what are the dimensions? So the final answer to this problem is a 10 centimeter by 10 centimeter rectangle. Or you could say a square, right? All right, let's go on to the next problem. Yeah?
What would happen if 10 was a max?
That's a good question. So let's say you do all your calculus and you get x equals 10 and you decide, okay, that's my minimum, but then you test it and it's actually a maximum. Then the question was a trick question.
And you can't find that out until you do the sign chart?
Yeah, isn't that weird? For example, what if the question had said, find the dimensions of the rectangle such that the perimeter is a maximum? That's actually a trick question, because I drew for you a minute ago a rectangle that was 100 spaces wide and only 1 space tall, right? I'll draw it here in red again. Remember my 1 by 100 rectangle? What was the perimeter of that thing? 202, right. What would have happened if I had just made this 0.5 and made this 200? What's the perimeter now? 401. See? There is no maximum. There's no maximum perimeter. I could then make this would be very silly, but you could do it. You could make this 0.1, and make the length 1,000, and the area is now 2,000 and 0.2, or the perimeter, I mean. See, so the perimeter keeps going up and up and up and up and up. And it would be a trick question, and you would need to know that. But the calculus will tell you all that if you do a sign chart in the end. Yes?
Can you explain to the sign chart really quick?
Sure. Yeah, we had one critical point at x equals 10. Just make sure you plug in meaningful x's, like don't try plugging in -1 and +1. We already said x is positive. So I tested 1 and 20 is what I tested. Yeah.
How would you respond if it was a trick question?
You would say this scenario has no such rectangle. Yeah, there is no such rectangle that has a maximum perimeter.
So don't say trick question.
Don't write trick question. Yeah.
It's like false.
Okay, now this is an absolute extrema problem, so we should be testing endpoints also. Okay, but the thing is there's no endpoint here. We said that x is a positive number, that means greater than 0. We're not going to allow 0, so we don't have to worry about that. From several of my drawings, you can see x can actually get as big as you want it to be. And so there's no meaningful endpoints in this particular problem. Okay, let's go to the next problem, which says, if oatmeal is 10 cents a yard, how many pancakes does it take to cover a doghouse? Oh wait, that's the wrong class. Sorry. That's not right. Why is that one in my calculus lesson? That was from my joke book. Oh. All right.
What a joke video.
Do you guys know the answer to that joke? Yes, he would. Yes, he would. If oatmeal is 10 cents per yard, how many pancakes does it take to cover a doghouse?
The limit does not exist.
D&E? Actually, the answer is none, because ice creams have no bones.
He's right. I should have no bones. It's like a true thing. It's an invalid argument.
Okay, there's a little Easter egg for my YouTube video there. All right. Okay, guys, so this one's this particular question, this one you kind of need to draw something because you're not going to be able to get very far at all if you don't. It's talking about a cylinder stuck inside of a sphere, and we'd like to know what the biggest volume would be. So you've got to draw a sphere. So I usually draw my spheres by drawing a circle. Some of you guys could train us all on how to draw spheres. And then I draw like an arc that way. Okay, so this is my sphere, like that, and I need to draw a cylinder inside of it, so why don't we use green for that, because green's cool. Let's see, do I have any cylinders in my little templates? No. Okay, that's all right. I will freehand a cylinder. Watch this. That's the top of the cylinder. There's a lateral edge like that. There we go. Okay, there's the bottom of the cylinder. Something like that. Okay, now the only given is that the radius is 10. So you probably remember this from taking the SAT or something. When you draw your radius, right, on inscribed figures, you can draw it wherever you want, right? The center to the edge of the sphere is the same in every direction. But it would be kind of silly to draw this radius. Like, that's not a very smart radius to draw, because it doesn't connect to the cylinder in any meaningful way. So can someone think of maybe a more beneficial way to draw a radius here? Yeah, try to draw from the center to the cylinder in this way. That's a little more meaningful. So that segment is half of the diagonal, I guess, for the cylinder. I don't know if cylinders have diagonals, but it's like half the diagonal of the cylinder, but it is simultaneously the radius of the sphere. So that's just a wise place to draw it. And that's 10. And there's nothing we can do about that. Okay? Okay, now, this gives us a little right triangle to look at. But there's no way on earth we can know the dimensions of that triangle because there are actually many possible drawings for this situation. We could also have drawn this same picture with our green cylinder sort of squashed like that. See? Don't draw this one. But you see, we could have drawn our cylinder more flat, you know? It doesn't have to be tall. In fact, we're trying to find the biggest volume cylinder that will fit. So is it that one? Is it this one? Should it be wide and short, or should it be, you know, tall and skinny? These guys see what I'm saying? There's actually infinite number of these pictures you could draw. So I cannot label the sides of these except with variables. So with that red triangle, I'm going to have to label one side x, just like I did in the video. Oops, that's not the right problem. There it is. All right, so let's go back to our drawing, and let's label this x. And I would really not want a second variable here. So I guess I could put y here for a minute, but isn't it true that x squared plus y squared equals 100 here by the Pythagorean theorem? Okay, so if that's the case, then why don't I just isolate y? There we go. I would rather use that than y. So I'm going to erase my y here that I had on my triangle, and I'm going to put square root of 100 minus x squared.
Would you have to put a plus or minus?
Not in this case, because it's just the height of a triangle, so we don't need a negative case. Good, good. Okay, my last thing before I get into the calculus is I need a meaningful constraint for x. X cannot be 1,000. X cannot even be 0. What values of x make sense and what values of x don't make sense? Like, you got to think about that. That's kind of like the natural domain of this ball. What's a meaningful constraint for x? X definitely has to stay less than 10, partly because it's a leg on a triangle whose hypotenuse is 10. So we cannot let it grow to be as big as hypotenuse. Good. That's an upper constraint. What's a lower constraint for x? 0. We cannot have a negative number, right, for a side length of a triangle. So we're going to stick to numbers between 0 and 10 when we draw our sign chart at the end of this problem. Everyone understand? Okay. Now we're ready to get started on the problems. We need a primary equation. What is it we're trying to maximize? Volume. So we want volume. We haven't even done that yet. Okay, so what is my primary equation? Primary equation is a volume equation. Volume of a cylinder is equal to what? Base area times height, right? So the base area is, of course, pi r squared. And then there's the height of the cylinder. So pi r squared h is always the volume of any cylinder. Okay, there it is. In my drawing, what is the radius of the cylinder? X, okay? So be careful not to interpret the r there as radius of the ball, right? So my volume function is pi x squared. What is the height of the full cylinder? Be careful. You've got two of those root 100 minus x squareds. Because the... What in the world? That is a really cool color, but I don't want it. Okay. Two of these make up a cylinder, right? So we're trying to study the green cylinder and write down its volume. So we got x for the radius, we chose that, and it's two of these heights to get a full cylinder. Okay, this is your primary equation in one variable, so you might as well title it v of x. V of x. Okay, why don't you just, like, work? Okay, that's not what I meant. That's better, thank you. No. Black is not the same color as white. So v of x. And let's write down that domain one more time. X is between 0 and 10. All right, let's go ahead and take our calculus into effect here. So it looks like it's going to be a product rule, right? There's a 2 pi right there. You can just kind of leave that out. Just leave the 2 pi chilling out front. But we need the product rule. So we're dealing with x squared and basically 100 minus x squared to the half. So I'll write the volume function one more time. It's 2 pi, and then we have x squared and 100 minus x squared to the half. And we need the derivative. So it's going to start off with 2x times 100 minus x squared to the half, plus, and then 1/2 times 100 minus x squared to the negative half, times negative 2x for the derivative of the inside, times the first function, x squared. I could probably just leave you hanging on this problem. Now that you know what to do, you're supposed to set this equal to 0, solve for x, blah, blah, blah. But since it's a fairly complicated one, let's finish it together. So here the 2's cancel out, but there is a negative right here, so watch out. So let's rewrite this before factoring it. There's a 2 pi, there's a 2x, there's a 100 minus x squared to the half, Then there's a minus x cubed, and then there's a 100 minus x squared to the negative half. And we've been working with these for a while now. We've talked about how you want to factor out this green thing right here. Remember that? On our last test, for example. So let's pop that out to the very, very front. And if you haven't gotten the hang of this yet, I can tell from some of your test corrections that not all of you do this. But I really think it's wise. You like to work with radicals and common denominators. That works too. The pie, I ate it. There it is. Now I'm hungry. Okay. So when you factor out that green thing, the first term on the inside goes up by actually it's going to drop. This is just going to become 100 minus x squared. And there's still a 2 sitting there. But it becomes, the half power becomes a 1 power. The idea is,
What about the other X? Did you eat that too?
I ate the x too. Hold on. I'm glad you guys are paying attention. Because in some classrooms it'd just be like, oh, teacher knows what he's talking about. But not here. Okay. There we go. Minus x cubed. Life is fun. Okay. Let's distribute that. We got a 2 pi. We know there's a square root of 100 minus x squared on the bottom. Okay, in the inside we have a negative 2x cubed and a negative x cubed. So there's negative 3x cubed. And then there's a plus 200x on the inside. Okay, we can also pull out an x real quick. So this is 2 pi x. And then we have basically 200 minus 3x squared. Okay, so what is going to make this 0? Let's look at our critical points. So critical points occur when x is 0, but we already said that was out of domain, right? We're not even going to allow that anyway. X is between 0 and 10, remember? Okay, and then the other one is whatever 200 minus 3x squared equals 0 gives us. So if we set that equal to 0, we get basically x equals the square root of 200 thirds. And I think I actually worked that out earlier. Good luck finding it. Anyone have a calculator? Yeah, I'm not going to find that in the next half hour. I had it right here, too.
Should we eat that one too?
I must have eaten that paper.
The numbers even taste good.
Not really. Okay, what's the square root of 200 thirds? Anyone got that? 8.16. I need 3 digits after the decimal for the AP test. They won't take anything else.
164.
So you truncated, someone else rounded. Okay. So this is inches, or maybe it was centimeters. Can't remember now. Was it centimeters? You should not expect a nice answer for everything, you know. But you could also write this as 10 times the square root of 2/3. And you multiply top and bottom by root 3, and you get 10 root 6 all over 3. You could do that. But, I mean, who talks like that, you know? Hey, build me a cylinder that's 10 root 6 over 3 centimeters wide, please. Nobody talks like that, right? So in geometry, we sometimes just go with the decimal, right? It's more meaningful. So here it is. Now let's go back and read the question. Did they want the optimum x, or did they want the volume of the cylinder, right? So going back, it says, what is the maximum volume? So we have a volume function. We already wrote it down. The volume function was 2 pi times x squared times 2 times the square root of 1 minus x squared. So now we just need to plug in that 8.164. And I would recommend that if you still have the 8.164 sitting on the screen, you actually type it like this to avoid errors. Use that answer button. You guys know what I'm talking about? The answer button is very, very accurate. So you've already got this just sitting on the screen. Just type this. It's the safest thing to do. It keeps all 10 digits or whatever and gives you a volume. Okay? So that's how you do that one. And don't forget cubic centimeters. They're very strict about units. And never use an equal sign when you mean squiggly equals. I mean it. Don't use equals if you mean squiggly equals. Can someone get us that number? And we'll be done.
If you plug in 8.164, don't you get a negative value?
This should have been 100, guys. Sorry, this is 100.
Isn't this supposed to be pi for the
Was there I knew there was a 2 here somewhere. Was it? There we go. It's the only problem with this little sketch pad is I can't go back up very easily. Okay, there, yeah, it's just pi times x squared times 2 times square root of 100 minus x squared. There we go. All right. So I mean, if you can do that problem, you can do any problem, okay? So, including this one here. This one here. If oatmeal's 10 cents a yard. So, that's an optimization problem too, I think. Okay, the sky's the limit on application. There's a lot of finance problems in the book, but we don't usually teach them because there's no finance stuff, it seems, on the AP test. But if you're doing business someday, you'll be taking a business calculus class and you'll be doing a lot of optimization. Okay, it's like the #1 topic, probably.
Did you please go back to the problems?
Oh, this problem? Or the one about the, oh, this one?
Yes.
Okay,
The bottom.
yes. I'm not making a sign chart because I don't believe this could possibly be anything other than my answer. The sign chart would show me that this was not a minimum volume. But listen, if I give you a ball and say, hey, build me a cylinder with minimum volume inside, you could just make its radius 0. You know? There's no minimum volume, but there's a maximum volume. If I give you a basketball and say, build a cylinder inside of it, it has the most possible volume, it has to be very well designed. So, okay, did anyone get me my volume? Non-real. It's because you accidentally typed a 1 instead of 100 right here. Oh. Okay. Well, this video will just have to not have an answer then. Okay.